It's my pleasure to introduce Basil Darby as he presents his master's thesis. An executive summary of this introduction: Basil was originally a particle physicist, but we managed to convert him into an oceanographer to help us learn about ocean dynamics. He received his BS from UC Santa Cruz in 2020 and continued to work after graduation there with the Santa Cruz Institute for Particle Physics. He later enrolled in our program at Moss Landing in 2021, but we had been in touch as early as 2019 when he started to think about possibly connecting physics with the ocean. When the pandemic hit in 2020, Basil and I reconnected about research, and he helped me add an ecosystem component to an idealized model that I was working on using his interest in dynamical systems. At Moss Landing, he's worked as a research assistant on a number of different projects. He worked in our lab's project on tidal fluxes in Elkhorn Slough, playing a really important role in helping to deploy a current meter in the slough and analyzing the data that came off it. He worked with Ching Wong's group, Air-Sea Interaction Group at the Naval Postgraduate School, going out to sea on the Sally Ride on that project. And he worked with Mike Wood and Dustin Carroll on modeling the California current system and the Greenland shells with MIT GCM. But despite having been involved in all those projects, Basil really forged his own path here at Moss Landing. He came in with a really strong interest in linking physics and dynamical systems, and has always sought out ways to try to independently develop his own thesis ideas. That included linking up with Dustin Carroll and plugging into the resources that are available through NASA that form the basis for his research. So as a result, he's developed a really novel and creative study linking sub-mesoscale dynamics with Lagrangian coherent structures. Basil will explain what all that means using rubber duckies as a prop. And if you tell Basil, it sounds very complicated, but if you tell Basil that something's complicated, he's all in on trying to understand it. He received a number of awards here at Moss Landing. He received the Archimedes Scholarship, MLML Wave Scholarship, and the Coast Graduate Student Research Award. And he recently just started a full-time job as an instructional lab tech at Southwestern College in San Diego. He's in the astronomy and physics department, and he has a lot of responsibility, including a planetarium, which I think is so cool. And it sounds like his background in oceanography will contribute a lot there as well. So without further ado, let's welcome Basil to present his thesis.
Thank you, Tom. Can you all hear me? Good? Cool. Thank you so much for that introduction. Like Tom said, there's a lot of very large, kind of scary words going on in the title. Don't worry, we'll get through them. There's a lot to get to, so without further ado, my project is on topographic and upwelling effects on surface Lagrangian coherent structures of Cape Mendocino. But first, before starting to kind of deal with more complicated things, let's start with the outline, just kind of see a path forward. So first I'm going to start to talk about coastal upwelling. I'm then going to talk about temporal and spatial scales in the ocean, more specifically the sub-mesoscale, the technique that I'm using, the Lagrangian coherent structure, my study location, then my science questions, quick model evaluation, filament evolution and depth structure, some Lagrangian coherent structure statistics, and then finally a possible connection to chlorophyll. So kind of arriving where we're at here, and you can even look behind you, and this is the beautiful California current system. I have in satellite image, a natural color image of the California coast. But as you can see, does this laser work? There's a lot of detail and complicated things happening in the ocean. Contrary to popular belief, there is a lot of things happening in the ocean. And so we, as physicists, like to sort of break things down in terms of spatial scales and time scales. So how do we do that? We create very large graphs with circles and arrows and point to them. So on the left, we have sort of the temporal scale of these different processes in the ocean, so ranging anywhere from seconds to tens of thousands of years. And then on the x-axis, we have the spatial scale, and so that's the sort of encompassing the entire globe down to more of what we see here of like the California coast. And so if you don't know, something very, very important to the California coast is coastal upwelling. It's a major portion of our sort of ocean ecosystem. And so every summer, there's a bloom that happens of phytoplankton, kind of linking physics with biological processes and even atmospheric processes. So on the left, I showed you this natural color image of the California coast, and then over here is the chlorophyll concentration of that same image of showing a phytoplankton bloom. So over here on our kind of spatial scale diagram, this process, this upwelling process, exists sort of right in the middle between the smaller scale molecular processes and then the big stuff that we care about, like climate change. So this middle scale, we like to call the mesoscale. Meso means middle. And so it has a tight kind of connection between physics and biology. Also, as physicists, we care a lot about the energy and how it moves throughout these processes. And we call it the energy cascades. So the energy of the ocean kind of flows down from larger scales down to even molecular. So I know a lot of you are familiar with coastal upwelling, but just a quick recap. So it is the interaction between the coast, the ocean, and the wind. And so right here, there's a wind vector going along the coast. That's just how the physics and average motion works out. That wind vector actually pushes the surface water away from the coast, displacing a kind of chunk of surface ocean water. And because water likes to kind of balance itself out, the only place that new water can come to replace it is the deeper, colder, more rich, nutrient-rich water comes to replace that. Then it is then utilized by phytoplankton, giving us these nice phytoplankton blooms. However, that is sort of the kind of basic approach we give about coastal upwelling. But if you noticed, there is lots and lots of detail sort of showing up in this coastal process. So we care a lot about this, since we care a lot about how energy transfers in the ocean. So these finer scale dynamics are not well understood because they evolve so quickly. It's like I mentioned, it's important to understand how energy gets distributed, and we know even less of that smaller scale in the on the coast. So I have an image of sort of some modeling experiments that was done in the California coastal region without the coast. However, you can see this sort of 12-kilometer resolution getting scaled down to a 15-kilometer resolution. That detail kind of just pops out at you. And so we really want to understand, so to have a better idea of how the ocean evolves and how the energy evolves in the ocean, we like to understand these smaller aspects. So this is called, because it's slightly smaller than the mesoscale, or the middle is, we call it the sub-mesoscale. So what is the sub-mesoscale? It's roughly about 100 meters to 10 kilometers horizontally, and about 100 meters to a kilometer vertically. These processes only last about hours to weeks. They consist of filaments and eddies in this sort of spatial range. And I have kind of imaged here, I believe this is in the Japanese Sea, or Japan Sea. There's a filament in the sub-mesoscale range, so in roughly 0 to 12 kilometers, and then there's also an eddy or a vortice. I also have another image to the right of a cyanobacteria bloom in the Baltic Sea. All I really want to show here is sort of this detail of swirling motions and these like filament structures that show up that can be seen given the kind of biology in the ocean. So if we look a little bit, or there's a label right here that says that's a ship. So if you can imagine people standing on that, you can see kind of more intuitively understand the scale range we're talking about. So quick submesoscale, or continued, we like to define, again, getting a little bit more complicated in terms of the spin or how much a fluid rotates. So quick recap on vorticity. So to the right, I have a vector field. So this is sort of how the ocean is moving on the California coast. And then on the color, we have what's called the vorticity. So if you remember righty-tighty, lefty-loosey, you take your right hand and you kind of look at where those arrows are curling. The positive direction is pointed towards you, and then the negative direction is pointed away from you, curling the opposite direction. So we define this sort of positive and negative as cyclonic versus anticyclonic. Cyclonic is in the direction that the Earth is rotating. So to kind of dynamically define what the submesoscale is, because there exists filaments and vortices in all sorts of different scales, we like to define the submesoscale as filaments and eddies as what's called the Rossby number of order 1. So it's the kind of local vorticity that the flow is going through, scaled with the rotation of the Earth. So we can kind of think, what's affecting the flow more? Is it like local processes like wind, or is it the rotation of the Earth itself? So we dynamically defined it, define it as rho. I'm going to interchangeably use vorticity, Rossby number, and relative vorticity kind of interchangeably throughout the talk. So if you see a graph with vorticity, I'm using rho. These sort of Rossby number order 1 have strong vertical velocities associated with them. And it's a kind of an open question of whether or not these strong vertical vorticities extend past the mixed layer, which we'll get to. So these features are hard to observe with satellites and ship-based sensors. So how can we isolate these features and investigate their impacts? With a reminder that if you imagine taking samples and trying to study these sort of filaments in greater detail is very, very difficult. But how? So this is where I introduce Lagrangian coherent structures, which is a cool method. In little oceanographic history, in 1992, there was a shipping container that fell off in the Pacific Ocean that released about 29,000 rubber duckies. But littering is bad. However, it allowed oceanographers to kind of trace where these rubber duckies ended up from a single starting location. So this is kind of what's called the Lagrangian perspective versus what's called a Eulerian perspective, where you just kind of put a sensor in the ocean and just kind of let the ocean go past and you measure it. You're letting yourself go with the flow of the ocean to see what happens. So with this Lagrangian perspective, you can define what are Lagrangian coherent structures. So these are structures that kind of appear within the fluid flow just based off of these particle trajectories. It's sometimes described as the skeletal structure of a fluid, and it's measured with the finite time Lyapunov exponent. So there's also the finite space Lyapunov exponent, which, again, physicists love to play with that space and time. But for the point of this talk, I'm going to kind of equate the two and just call it Lagrangian coherent structures. Right here is a sort of a vector flow map of, we would imagine, the surface ocean. And so let's imagine a large shipping container gets released into the ocean at a specific point, and then we're just going to let those rubber duckies evolve with time and follow the arrows, or the velocity vectors, pretty much. So as it moves on, it kind of moves, or these duckies move away from that initial release spot, and you can sort of notice that these duckies are being attracted to that x-axis. So this is great because we can define our attracting Lagrangian coherent structure as that x-axis. So you'll notice again, though, that not only are these being attracted to sort of this x-axis and then won't pass it, they're being repelled from the y-axis, which is a repelling structure. And so, like a skeleton, you can see it's sort of defining how, without knowing the velocity vectors, you can sort of see how particles may behave just from these structures themselves. So LCS has been studied in the California current system. This is Giddings 2022. They found there is a high intensity of Lagrangian coherent structures. They integrated over about 4 kilometers and 12-hour temporal scale, which, if you remember from the time and space scales, that doesn't necessarily relate exactly to the subbasal scales, but they instead they only mentioned the mesoscale. These are defining the mesoscale features in the California current system. And they found a very strong correlation between the structures, the structure's intensity, upwelling, and was positively correlated with chlorophyll. The strongest intensity and annual consistency being around Cape Mendocino. So this looks like a great, because it's the largest intensity of Lagrangian coherent structures, Cape Mendocino makes a great place to study this. So it's consistent not only in these structures, but in terms of its upwelling dynamics. So every year it will have an upwelling season around summer. It has consistent spatial dynamics, meaning there's a distinction in the coastline between south of the Cape and north of the Cape. Again, it's upwelling, so there's a rich biogeochemical physical connection to this upwelling front, and is a great place to study the submesoscale. Over to the right is a satellite image of SST. You can already see that cold upwelling front sort of interact with the warmer offshore water, creating like this mixing area. And you can see this mixing area is very distinct from what's going on north of the Cape. So this leads to my science questions. Does attracting Lagrangian coherent structures and repelling structures relate to the submesoscale? How do these structures evolve in time relative to Cape Mendocino? What are some mechanisms, or how deep does their influence go? And then what are some mechanisms of their generation in relation to the upwelling front? And then finally, do these structures in particular relate to chlorophyll? So that was a nice kind of introduction to the kind of key aspects, a lot of moving parts to this project. So for the rest of the talk, I'm going to be talking about the model I used, its evaluation with observed data, some time series results, the filament case study, or a filament case study, its depth structure, its relative, or its associated depth structure, the vorticity, or the Rossby number at these attracting and repelling structures, and then finally, a possible connection to chlorophyll. So for this project, I used the LSC 4320. In classic NASA fashion, it's a lot of acronyms and numbers. However, it is a global model with, in this location, roughly a resolution of about 1.8 kilometers. Also a nice part about this model is that it has hourly data, so it's hourly and global. But given that it has such high resolution and it is global, it was only run for about 14 months. This model is not adjusted to match observations as it runs out, so it's just a forward-running model. So we have a lot of stuff to get to, so I'm going to quickly go through the model evaluation. So we took a temperature and salinity kind of CTD CAS from this Trinidad cruise data, which is outlined with this red circle. We also used high-frequency radar velocity to kind of match or evaluate the velocity of the surface, which are right here. And then we also used a satellite product of SST, which is the NASA's MER satellite SST product. Quickly going along, we find that the cruise data shows a stronger agreement at depth than at the surface, kind of telling us that there's a diffuse mixed layer in the model compared to what is observed. On the right, we have the model temperature, on the y-axis, we have the model temperature, and on the x-axis, we have observed. You can see there's a slight warm bias, and then it just kind of goes crazy as we get to the surface. We find there's a reasonable agreement with HFR velocity data and the model data, even though we have sort of this patchy data availability in the HFR radar arrays. We find that, or I find that the R-square value of comparing the MER SST to the model SST kind of gets a little bit worse towards the coast. However, there is more, because of that upwelling front, there is more chaotic behavior more towards the coast, so you can't get that kind of one-to-one matching properly. Kind of concluding with the model evaluation. So given that we're using a model, it's important to remember that this may not represent reality. The SST does worse near shore, but better on average. The mixed layer is more diffuse, and then the velocity in the model has a higher magnitude than HFR and a slightly different direction. This means that structures generated in the model could be stronger or exaggerated, more exaggerated at both the surface and depth. But if we look at sort of a snapshot of satellite SST, we can see agreement with more of the structures generated. So over here on the left is a satellite image of SST, and on the right is SST from the model itself, and you can see an upwelling filament and then an associated upwelling filament over here. So moving on to the Lagrangian coherent structure method. So I have my collection of rubber duckies that I place around the cape. I let it evolve through time, calculating the finite time Lyapunov exponent. Looking at the kind of bright spots or ridges, I can then select for where the attracting and repelling Lagrangian coherent structures are in terms of points around the cape. So I did this with a 6-hour integration. This was due to some structures observed in this sort of area, or submesoscale structures kind of exist in that time frame, with reseeding sort of happening restarting every 6 hours. We can use these points then. So this gives me a collection of points associated with attracting structures versus repelling structures. So I can then use these coordinates basically to look at other properties of what might look, or what other properties might look like at these locations, like vorticity, which we care about. And we can also look at the total time series of these structures to see if there's any seasonality with these structure generation. So I'm first going to start with this time series results. So I separated out north versus center versus south of the cape. And over here I have the normalized to area, the amount of Lagrangian coherent structure points relative to that north, center, and south points. And down here, I have the northward wind stress. In the California current, it's important to note that when this sort of northward stress becomes primarily negative or southward, that determines upwelling. So we can see that in November, so December, and then when 2012 starts, this is sort of the winter storm period with a sort of transition area, and then primarily the upwelling time period. And we can see that in the LCS point data. So this means there's strong seasonal signals with LCS. It appears that the strongest sort of pulse signal happens during the upwelling season, which is over here. And then primarily the amount of Lagrangian coherent structures is primarily that north to center area. So I'm very interested in these like sort of larger pulses. So maybe we can investigate further and to see what sort of is going on. So this leads to our first case study, which is a upwelling filament. So what I'm showing here is the upwelling front sort of being evolved with time, just north of Cape Mendocino. This is Cape Mendocino. A eddy that's pinching off of that upwelling front. It's strongly filamenting out, and then finally sort of disintegrates and goes away. I define, so there's kind of three distinct phases of this filament evolution. We have its birth phase, its coherence phase, and then its death phase. We care a lot about vorticity, so let's then look at that same animation in terms of vorticity. So this would be that upwelling front. We can see large vorticity on that kind of edge right there. This eddy that starts to pinch off from the upwelling front. Filamentation, filaments out, and then finally disintegrates or dies. I don't know if that's morbid or not. But we can see a lot of very high vorticity values that is indicative of the submesoscale. So now as a Lagrangian coherent perspective, that same evolution is quicker because it's 6-hour time steps. We can see that filament gets selected for with these kind of quick LCS points. And so these LCS points find areas of high vorticity, and they also seem to be areas of high filamentation, where there exists that large gradients of density, meaning cold, rich, upwelling water versus warmer away from shore water. So looking closer at that surface filament, I have mapped the Lagrangian coherent structures of the attracting and repelling ones over the temperature field for the upwelling filament. And we can see it's slightly off from the core of that upwelling filament, which to me is very interesting in terms of how spatial scales may be related. But let's first look at how it may be distributed with depth. So this red line that I have in both the left and the right graph are these cross sections. So if you imagine a sort of cube, I'm slicing kind of vertically where these red lines are. And so we can see the mixed layer goes to about 50 meters. And right where that upwelling filament is, we see a large perturbation in the mixed layer over here. And then to the right, we have that same sort of cross-section, just a little bit to the core of the filament. And then instead of where the core of the upwelling filament is, we see the largest sort of perturbation happen, not here, but where our attracting and repelling structures are. So moving on to relative vorticity of depth structures. So right where we find those attracting structures, we also have very high relative vorticity going past that depth, or that mixed layer, down to about 100 meters over at the tip of the filament, and then over here at the core of the filament, not necessarily at the core, but where the location of the strongest attracting and repelling structures are, we find strong relative vorticity going again to that 100 meters past the depth, the mixed layer. As I mentioned, submesoscale processes have very strong vertical velocity, and so beginning to sort of connect these dynamically defined, Rossby number order 1 to Lagrangian coherent structures to strong vertical velocity, we do find, yes, there is very strong vertical velocity reaching past the mixed layer at locations of attracting and repelling structures. This is slowly starting to convince me, again, I mean, I'm giving this presentation, but To me, this seems that there is this sort of interaction of the submesoscale with Lagrangian coherent structures. So just to kind of give you this full rundown to see everything kind of matched up. So LCS aligns more with the high vorticity edge of the filament instead of the core. This could be because of separation of scales. So instead of this being a submesoscale filament, it's more likely that it is a submesoscale front on the edge of a filament, kind of going to how messy things get as you get smaller and smaller and smaller, and how things kind of interact. This vorticity and vertical velocity reach below the mixed layer, and these upwelling and downwelling patterns seem to match more idealized studies of the submesoscale. So this is a diagram of sort of a submesoscale front. So we have strong upwelling and downwelling locations. So this is more dense water, and this is more lighter water. As I mentioned, it has strong vertical velocity, and this strong vertical velocity could contribute to nutrient supply to the surface water, so kicking up more of that colder nutrient-rich water to the surface where it can be utilized by phytoplankton. And so all I want you to kind of focus on is this sort of pattern of downwelling on the left and then upwelling on the right. Because how may this sort of more idealized diagram relate to our Lagrangian coherent structures, which we've become very familiar with? So this is how I kind of think it should behave. You have a downwelling side where on the left you have an attracting structure, and on the right you have a repelling side where that water comes up and sort of separates away towards the surface. So this is kind of how I imagine it should look. And going back to our surface image and our vertical velocity, we see that on the left we have intense downwelling, and if we kind of squint, we can see these attracting structures on the left and then a repelling structure on the right. And yes, we see a downwelling on the attracting side and an upwelling on the repelling side. And over here, it's a similar story where on the right we have a repelling side, on the left we have an attracting side, kind of further illustrating that connection between the submesoscale and these structures. Sorry, I'm going to start going quicker because there's still a lot to get to. Over here, I mapped the repelling structures and attracting structures onto vorticity just to kind of see if there's a pattern going on, whether or not attracting versus repelling prefers cyclonic versus anticyclonic behavior. So we see that attracting sort of sticks more to this negative vorticity, and repelling sticks more to positive vorticity. And so a question that kind of naturally comes up is this a fluke? Does this kind of come up elsewhere? And so that's when we look at statistics, which is a very fun subject. So down here, I have sort of collected all of the points of attracting and repelling structures, and I sort of map onto those points onto vorticity, and I add all of them up and see where the most sort of probability hits of attracting versus repelling structures. So this means that at a attracting structure, you'll find a higher probability of more negative, and then over here, at repelling structures, you'll find a higher probability of more positive vorticity. So other people have looked at sort of the statistics of submesoscale variability. Over here is an image from Sherbina. They looked at both a model distribution and observed distribution of submesoscale behavior, and we find that this sort of curve of probability shows surprising agreement with attracting structures, meaning that attracting structures do sort of do select for some sort of submesoscale variability. But what's interesting further, so that's this guy, but what's interesting further is this positive kind of bimodal distribution on the repelling side. So both of these are skewing more towards order 1, so indicating a submesoscale connection. But I want to see whether or not this sort of distinction further lasts throughout the entire time series of structures that I've looked at. So that's this graph. We have time on the bottom. We have relative vorticity here, and then the heat is the probability of that sort of vorticity value. We have attracting structures on the left, and we have repelling structures on the right. These probability distributions retain their shape over the course of the entire time series, which is also further indicating that it selects for like a specific range of behavior. And if we look closer, we see that there are these distinct excitation events that it sort of doesn't really have a lot of negative vorticity, but has strong positive vorticity. And so I kind of tricked you. This is our upwelling filament that we've become so familiar with. And so it seems as though we can see active filamentation or active submesoscale behavior through the probability of repelling Lagrangian coherent structures. So these excitation events have high vorticity. They have strong vertical velocity that maybe, I'm not sure with all of them, but in particular this one reaches past the mixed layer. And so because of that deep influence of maybe kicking up nutrient-rich water, do we see this sort of patterning with chlorophyll? And so up here is that image I showed earlier of the upwelling filament in terms of SST for both observed and the model. This is actually our observed counterpart of the upwelling filament that we've become familiar with throughout this talk. And down here, I've mapped the observed chlorophyll concentration with that observed counterpart of the upwelling filament. Zooming into it, there is a lot of detail kind of coming off of that upwelling filament. Now, is this patchiness or detail further down the upwelling front a indication that it is the strong upwelling associated with the submesoscale? I'm not sure. That is a future kind of aspect of where this study might lead to, looking at more of the statistics of relating chlorophyll and these Lagrangian coherent structures. So with that, some future directions is that those chlorophyll statistics, linking kind of HFR Lagrangian coherent structures with more model-derived Lagrangian coherent structures. There's a question of whether or not it's better to evaluate a model's velocity field with these structures versus just comparing the velocity fields. The LSC 4320 is a global model, meaning that we can kind of use this analysis to look at the global coast of submesoscale behavior and Lagrangian coherent structure behavior. We can then look also at more kind of these case studies. So in my study, I didn't show the other one, but we looked at 2 case studies of how this relates to filamentation. And then finally, we only used a surface Lagrangian coherent structure method. There is a 3D Lagrangian coherent structure method that we can do to kind of probe further because the submesoscale is a 3D process. So with that, I'll give you some takeaways. So short time Lagrangian coherent structures, with this sort of finer scale resolution, retain a strong seasonal patterning. These statistics that we looked at match those of sub-mesoscale variability. In summer, this variability can be connected to strong filamentation events, specifically pointed to attracting and repelling structures. These structures can indicate areas of a mesoscale to submesoscale sort of transition area, so that difference between the upwelling filament and that smaller submesoscale front. And these patterning of attracting and repelling structures kind of close together can indicate areas of strong upwelling and downwelling, which, if we extrapolate what we find here to more of those excitation events, possibly they all go past the mixed layer, but that requires further investigation. Finally, these strong vertical motions could contribute to nutrient suppression or supply. So if you notice, there was both upwelling and downwelling, meaning that with upwelling filaments, you could have some more of that patchiness show up as it gets evected offshore. And with that, I'd like to acknowledge my committee, so Tom, Dustin, and Max. Thank you so much for allowing me to kind of take an idea and sort of run with it. I'd like to thank the PhysioSh Lab for their support. I'd like to thank the Cool Group, the Computational Oceanography Lab, for working with them. I'd like to also thank the MPS Boundary Layer Processes Group, so Ching, Dave, Ryan, and Jesus. I meant to put this up there, but I was able to go to the Echo Hack Week, and so we just worked with the Echo product or Echo modeling product, which was very fun. And finally, thank you to Coast for funding a portion of this research, and then also to my wonderful partner, Lynn, to my friends, my little brother, my parents, Katie, Nick and Ocean, my cohort, Adam, Miles, Bradley, everyone. Thank you so much. Questions?
We have some time for questions, and so we'll have a question and answer session. I'll pass around the microphone. This won't amplify your voice. It's just for the people on Zoom. And after the questions, Basil will meet with his committee, and then we'll celebrate. So, any questions?
There's also rubber duckies over there after. Jesus, too.
Hey, Basil, good talk. I just was curious about your bimodal distribution and your repelling, I forgot what you call it, RLCs. Mm-hmm. And I was just wondering if there's any, does that mean that there's some, I guess that would be downwelling within that filament that's happening? Is that the case?
Yeah, so just with how that filament was sort of mapped out, the attracting structures were more related to downwelling, and then the repelling structures were more related to upwelling. So I guess this would indicate there's a higher probability of attracting structures, meaning it's more likely you'd find downwelling, if we were to sort of use that case study as an example. Does that answer your question? Okay.
Hey Basil, great talk. This is an impressive amount of work. It's always interesting to see a LCS study, and you did a lot with this. This is great. Yeah. I had a couple questions, but I had a kind of a basic one about your mixed layer depth. When you looked at the perturbations of the mixed layer depth, and this is in the model, correct?
Correct.
So my question was, I mean, these are very large perturbations to the mixed layer depth, and I was just curious.
Yes.
I know it's in model world, but and I know you probably don't have observations to kind of corroborate this with, but have you looked at some observations just to see order of magnitude that those perturbations are physically reasonable?
I don't think there's, I don't have observations of those types of perturbations in the mixed layer, specifically in this region. However, the mixed layer itself is sort of more diffuse in the model, and so it could be exaggerated versus like more, if we were to go out there and actually observe and take like a transect or something, we might find that these perturbations do happen, but just slightly less. Does that answer your question? Yeah, no, it does. Okay.
Wonderful presentation. I had a kind of just a general question, and so your study was specifically looking at like Cape Mendocino and specifically like upwelling and downwelling. Do you think similar relationships could be found with submesoscale features in like LCS in like open ocean conditions as well?
So from what I remember, open ocean, so that probability distribution that I compared my probability distribution to was statistics in the open ocean, specifically south of the Gulf Stream. And so I know that there are some studies that suggest open ocean submesoscale motions contribute more to like downwelling or like suppression. But I'm sorry. Does that answer your question, or could you repeat it? Yes. So correction, I did not mention that. Good catch. So yes, that probability distribution that I showed was a open ocean distribution and not specifically on the coast.
Good job, Basil. There was a really interesting paper I was thinking about that I think Brock Woodson published that was looking at how recruitment of invertebrates and fish on the coast is highly correlated with the probability of there being an upwelling front present on the coast. And so I was wondering, as you're thinking about some of the work that you did, do you think it's sort of the presence of these Lagrangian structures that are helping to, I guess, aggregate larvae out there, or increased productivity, maybe influencing their survival, or some combination? I guess, it'd be fun to hear you kind of talk about the connections between your work and like what's happening with the biology
so
and stuff.
I have also seen studies of like attracting Lagrangian coherent structures being sort of hotspots for biological activity, and so it's I don't know. I think it's still an open question whether or not the I guess aggregation of larvae is what you're mentioning, is more associated with like it traveling along that, this for example, traveling along one of these like upwelling filaments, and kind of getting stuck in that that dense core, versus if it just so happens to touch a attracting structure, then it will be strongly sort of attracted to that as well. So it's a very good question. I'm not exactly sure, but definitely interesting further research. Yeah.
I have a question, Basil.
Yeah.
So you mentioned you did 2 case studies. So for those people who aren't going to read your entire thesis,
everyone should.
Yeah. Definitely should, but could you give people a quick summary of what are the differences between the filament you looked at and the eddy that you did?
Yeah, so the second case study that we looked at was, actually there's a nice image of Cape Mendocino with this sort of eddy south of the Cape. So sort of mesoscale eddy, just to kind of clarify, this mesoscale eddy, I circled it, was our second case study. So we're seeing how sort of the Lagrangian or the attracting and repelling structures sort of behave. And we found that a lot of those excitation events or filamentation events happen on the boundary where we get that large distinction between more dense water, the upwelling front, and then less dense water out here. And so one of those excitation events, this image is actually very useful because we see that there is a upwelling kind of filament kind of coming out and then going along that eddy boundary. The LCS structures, so just looking at mapped LCS structures and vorticity, found one of these upwelling filaments just on the edge of the eddy. And so I was already sort of looking at that upwelling filament north of the Cape because I found it and then started doing stuff. But then I saw an excitation event. I'm like, what's that? And it just so happened to be a upwelling filament. I may have gotten a little sidetracked. Is that cool? It's really exciting. It's really fun. Just to see like data can kind of point to areas of really exciting behavior. Yeah.
And we have one question online from Tim Stanton who
Yeah.
asked, how do the LCS maps compare with the divergence field?
Another very good question. So in the upwelling filament, locations of divergence were associated with upwelling, and locations of convergence were associated with downwelling on the surface. So there is, so convergence is when water sort of goes in on itself, and then divergence is when water goes out on itself. When you have a 3D process, or when you have like a 3D field, if you're just looking at the surface and you see a divergence area, you can kind of guess, well, okay, water might be coming up and then diverging outward on the surface because it's got nowhere else to go. And so we did find a relation between repelling structures and attracting structures in the divergence and convergence field. The statistics don't work out as nicely as they do vorticity, but in particular, the sort of edge of the upwelling filament, you did see that pattern, just not at the total. It doesn't work out with the total statistics that way.
Very nice talk. I guess during your PhD, it happened too late for you to use, but there was this big NASA experiment, the submesoscale.
S-mode?
S-mode.
Yeah.
Did you ever look at any of the data, or okay? So
S-mode happened like just south of my like study domain, and so yes, I was really excited to see all of that data happen. Unfortunately, I was not able to use it, so maybe in the future I would love to use it. Dustin.
Very nice presentation, Basil. If you were to have a project funded, you could do your dream observations in this region. Can you speak or just kind of speculate on some of the key elements you'd want to deploy to observe these features and link them to the model?
Yes. I would, so one, I would like to have 3D 6-hour Lagrangian coherent structures all along the California coast within a given model, and compare it to as much sort of data of chlorophyll as possible, just to sort of probe deeper into that connection between the submesoscale and like phytoplankton blooms. Because it is still an open question of whether or not this water is just moving already existing populations of phytoplankton around versus it's actually contributing to the nutrient supply or the nutrient suppression in a significant or maybe just a tiny portion of maybe the nutrient budget itself.
Great, thanks.
Yeah.
Okay. Well, Basil's going to meet with his committee, but feel free to stick around. We have some snacks and refreshments, and we won't keep them too long. And let's give Basil another hand.
Thank you. There's rubber duckies. Please feel free to take one as a souvenir. Oh yeah. Yeah. Oh, I should have. Yeah. Oh, that's such a perfect opportunity. Darn.